We all think we know what force is. A push, a pull. The strain in your arm when you shove a heavy box. But a body on a ramp slides on its own. A dropped ball speeds up with nothing touching it. So what is force, really? Newton gave the answer a precise mathematical form. In everyday language, force is the effect of a person's strength. Galileo saw more. In his 1623 work Mechanics, he spoke of a force acting on bodies on inclined planes and in free fall when no one is pushing at all. Then in 1687, Isaac Newton published his 3 laws of motion in the Principia, the mathematical principles of natural philosophy. His first law captures the key idea. When no force acts on a body, it stays at rest or keeps moving uniformly in a straight line. When a force is applied, the body changes its state of motion. Force is whatever changes motion. Newton's leap was to tie force to acceleration. Earlier thinkers, Galileo among them, knew force produces motion. Newton extended force to any circumstance that produces acceleration. Start a body from rest and it accelerates in the direction you push. If it is already moving, the force can change both its direction and its speed. In Newton's own words, an impressed force is an action exerted upon a body to change its state, either of rest or of uniform motion in a straight line. Here is the crucial choice. He defined the force on an object as proportional to that object's acceleration, not to its speed, not to its position, to how its motion is changing. To turn proportionality into an equation, Newton needed a constant of proportionality. He called it the quantity of matter, what we now call inertial mass. He described it as the measure arising from a body's density and its bulk together. So air of double the density, filling a double space, holds 4 times the quantity of matter, filling a triple space 6 times. The same rules hold for snow, dust, or powders pressed together. And this quantity, Newton noted, shows up in a body's weight, proportional to it, as he confirmed with careful pendulum experiments. Now we make it precise. Apply a force to a chosen standard body. Measure its acceleration magnitude with an accelerometer, any device that reads acceleration. We define the force magnitude as the standard mass times the acceleration magnitude. That definition fixes the magnitude and the direction of force. So force is a vector, but a claim needs proof. So we run an experiment on the standard body. First, apply force 1 alone and measure acceleration 1. Force 1 equals the standard mass times acceleration 1. Next, apply force 2 alone and measure acceleration 2. Force 2 equals the standard mass times acceleration 2. Now apply both forces at the same time and measure the combined acceleration. By our definition, the total force is the standard mass times the combined acceleration. Then we compare. Experiment after experiment shows the combined acceleration equals acceleration 1 plus acceleration 2, added head to tail as vectors. Multiply through by the standard mass and the forces must add the same way. The total force equals force 1 plus force 2. That last line is not a definition. It is a consequence forced on us by the experiment. Let's put vectors to work. Here is example 7.1. 2 ropes are tied to a post of mass 1 kilogram stuck in the ground. The ropes pull the post and the gravity pulls it down. We're given the rope forces as vectors in newtons. Force 1 is 70 newtons in the x direction plus 20 newtons in the y direction. Force 2 is negative 30 newtons in the x direction plus 40 newtons in the y direction. The gravitational force from the Earth is negative 10 newtons in the I direction, straight down. Our goal? Find the magnitude and direction of the force the ground exerts on the post. Here is the idea. The post is stuck, it isn't accelerating, so all the forces on it must cancel. Let force 3 be the sum of the 2 rope forces and the gravity. Add the x components, 70 minus 30 gives 40 newtons. Add the y components, 20 plus 40 minus 10 gives 50 newtons. So force 3 is 40 newtons in the x direction plus 50 newtons in the y direction. For the post to stay put, the ground force must exactly oppose force 3. So the ground force equals negative force 3, negative 40 newtons in the x direction and the negative 50 newtons in the y direction. It points down and to the left. Now its magnitude. Take the square root of the sum of the squares. The square root of negative 40 squared plus negative 50 squared. That's the square root of 1600 plus 2500, the square root of 4100, which is about 64 newtons, and its direction. The angle below the horizontal is the inverse tangent of 50 over 40, which is 51.3 degrees. So the ground pushes back on the post with a force of about 64 newtons, directed 51.3 degrees below the horizontal, down and to the left. Notice the post's mass, 1 kilogram, never entered the arithmetic. That's the whole point of vector force. We just added the pushes and pulls component by component, and the answer fell out. One more use of this definition. So far, the standard body only measured force, but we can also weigh any other body against it, and we call the result the inertial mass. The procedure: apply a known force to the standard body and measure its acceleration, call it A sub s. Then apply the same force to an unknown body and measure its acceleration, A sub in. Since the same force acts on both, force equals the unknown mass times A sub in, and also the standard mass times A sub s. Set them equal. Rearranging the ratio of the unknown mass to the standard mass equals the inverse ratio of the accelerations. So the unknown inertial mass equals the standard mass times A sub s over A sub in. A bigger acceleration means a smaller mass. Repeat with a different force and you get the same ratio. So here is Newton's concept of force in 3 pieces. Force is inertial mass times acceleration, with mass, the quantity of matter, as the constant that turns a proportionality into an equation. Force is a vector because the accelerations it produces add head to tail, and so the forces add the same way. And that single relation lets us calibrate any mass in the universe against one standard, from a push and a pull to physics. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.